Okay, guys, so here we go. We're talking about today how they find these atomic masses for these elements. So again, one atom of phosphorus does not weigh 30.974 AMU. One atom of sulfur doesn't weigh 32.066. One atom of arsenic doesn't weigh 74.922. And one atom of any of these things doesn't weigh what these masses are telling us. What these masses are actually a weighted average of all the possible isotopes of the element, or all the isotopes that are in existence in nature of these elements, okay? And anywhere you look in nature, the ratio of isotopes is pretty consistent. It's pretty consistent, okay? So for example, here we have chlorine. 75% of all chlorine atoms weigh 35 AMU. Okay, that means they have 18 neutrons and 17 protons. 17 protons, 18 neutrons. And 25% of all chlorine atoms have 17 protons and 20 neutrons to make 37, a mass of 37 AMU. Okay, so when we take this weighted average, so if we were to take a whole bunch of chlorine atoms, weigh them, and then divide by the number of chlorine atoms, we'd get a weighted average, or an average, of 35.5 AMU. Okay, now you'll notice that this number is closer to 35 than 37 because there's more chlorine 35s in nature than there are chlorine 37s. Okay, so it's not exactly in the middle because it's not a perfect average, it's a weighted average. Okay, so if we want to find a weighted average, or the atomic mass of a given element, we have to look at the isotopes and their percent abundance. Okay, and we're going to do a weighted average of this to find the average atomic mass. So weighted average. And the formula for a weighted average is really, really simple. It's percent abundance times the mass of each isotope. Percent abundance times mass plus percent abundance times mass. And then we'll get the atomic mass for that element. Okay, so for example here, we put the percent abundances, we put them in decimal form. So I moved the decimal over twice because I divided by 100. So this one's 0.9223. This one's 0.0468. This one's 0.0309. Okay, so we take the percent abundance in the decimal form, multiply by atomic mass, and do that for each one of these and add them up. So here we have 0.9223 times the mass, 27.97693, plus the other one, 0.0468 times 28.97649, plus 0.0309 times 29.97377. Okay, so we multiply that and we add it up. So let me do that real quick. Okay, so I got 28.085. Okay, which makes sense. Okay, it's somewhere in between all of these numbers. It's somewhere in between the lowest and the highest number, and it's closest to the one that has the highest percent abundance, so it's closest to 27.9. Okay, so this is 28.8085 AMU. So that'd be the atomic mass of that. Okay, so next, we'll do the next one. If you want to pause this for a second and try it on your own, go ahead and do that. Otherwise, I'm just going to keep going. So here again, we're going to convert these to decimals of 0.6917, 0.3083. Okay, and then we do percent abundance times mass, so 0.6917 times 62.9396 plus 0.3083 times 64.9278. Okay, we do that math here and we'll get the answer. Okay, and the answer is 63.553 about MU. Okay, Let's check, make sure it's between these two numbers. It is, and it's closer to the one that's a little bit higher percentage. So that looks about right. Okay. Next type of problem here is we're trying to find the percent abundance of each of them given two isotopes and the atomic mass. So this we need to set up a system of equations. First of all, we say that X is the percent abundance of 151 and Y is the percent abundance of 153. And the 2% abundances added together should equal 1. So X plus Y equals 1. And then we should also know that 151 times X plus 153 times Y equals the atomic mass. So equals 151.97. Okay, now we're going to use substitution to solve this. So we're going to subtract Y here, subtract Y, and solve this equation for X. So we know that X equals 1 minus Y. Then we're going to substitute for X, and we're going to put 1 minus Y. So here, instead of X, we're going to get 151 times 1 minus Y plus 153 Y equals 151.97. And we're going to solve for Y here. Distribute. So 151 minus 151Y plus 153Y equals 151.97. Okay, combine like terms. We get 2Y. Subtract this from both sides. We get 2Y equals 0.97. Divide by 2. Divide by 2. We get Y equals 0.485. Okay, and then in order to find X equals 1 minus Y, or 1 minus 0.485, we get 0.515. So again, these are the X and Y are the percent abundances in decimal form of each isotope. So 151 has a percent abundance of 51.5%. And I'm just moving the decimal 1, 2 over, and I get that 51.5%. Copper 153 has a percent abundance of 48.5%. Okay, these percentages should always add up to 100%. And you're always going to have a larger percentage of the one that's closest to the actual atomic mass. So this 151 should be the higher one because it's a little bit closer to 151 than 153. Okay. Okay, so if you want to take a minute and try and do this one, you can. And then you could stop the video and then try it and then restart the video, and I'm going to go over the answer. Okay, so I'm going to go over the answer right now. So again, we have X plus Y equals 1. They have to add up to 1. We have 63 times X plus 65 times Y equals 63.55. Okay, do our substitution thing again. So solve for X. X equals 1 minus Y, so plug that in. 63 times 1 minus Y equals, oh, sorry, not equals, but plus 65Y equals 63.55. Okay, then distribute. 63 minus 63Y, 65Y equals 63.55. Combine like terms and solve for Y. So minus 63 minus 63. This is 2Y equals 0.5. Divide by 2, divide by 2. Y equals 0.275. Okay, then again, X is 1 minus that. And we get 0.725. So we know that the percent abundance of 63 is 72.5%. And 65 is 27.5%. Now we just look at our answer. It's 63 it's closer to 63 than 65, so 63 should be a larger number. It is, and it should be significantly larger because it's much closer. So I'm going to say that's probably the right answer there. Okay, that's it. If you're still having trouble, let me know, and we can work on some more of these. All right, see you later.